Alright, welcome back to Meteorology 101. So, visit my website, meteorology101.com. Help me get some traffic over there. We're going to jump into the models in a little bit, current weather conditions. So, first thing we need to do is find out what's going on real time. Anytime before you jump into the models and start running the model loop and trying to figure out what's going to happen in your area, first thing we need to do is look at what's happening in real time and then verify those models. So I'm not going to get too deep into verifying the models. I never do. I pretty much look at satellite, radar, and then if there's any significant areas in the United States that I need to get closer to the radar, then I'll look at that. I do look at a surface chart and then see what pressure systems are out there. And then if I have to get deeper into those, then I'll go into the upper levels. So you want to break those systems down. How intense are those systems? What is happening real time before you get into the models and start just forecasting right off the models? I see that everywhere on the internet. Everybody forecasts off the models. The models are great. It's a great tool. They work. The closer you get to the storm that is approaching your area, the better they work. But learning how to verify those models and just look at real-time data will get you a long way. Understanding what the atmospheric dynamics, what's happening in the atmosphere, that's going to get you a long way. To one, forecast a low pressure system that the models aren't picking up. If a low pressure system develops over Texas, why is it developing over Texas? Is one going to develop over Texas? Maybe the models have missed it. Next thing you know, you have a low pressure system over Texas, moving to the northeast, and you're getting hammered. So we just want to look at these features on the satellite, what these tools are for, and then look at the national radar. And then if, like I said, if we need to break it down, we'll go to zoom in on the radar. So I usually start with a satellite just to get an overall picture of what's going on. This is going to give you an idea where the lows are, where the highs are, and what kind of significant weather is occurring right now. So if we look at this, let me get my draw tool here. So this is just a second. This satellite is a geocolor, true color daytime. It looks realistic during the day. Multispectral IR at night. So as you see the sun, as the sun sets, you can see the line. You can see how it changes color. So you're going to miss a lot of the low-level features at nighttime on this. So you kind of pick them up as the sun goes past. So you can go to IR, you can go to visual during the day, or you can go to IR at night, and you can pick up those low-level clouds on different IR spectrums. So right now, I'll use this tool for, unless I'm getting into breaking down a storm and I want to see exactly where the cells are developing, then I pretty much just look at this for an overall tool. So let me get into the draw tool here. Alright, so the first thing I'm looking for is rotation. So we have possible jet finger, a little bit of a frontal system or something going on there, or maybe just a minor shortwave trough. You can see the southerly flow off the west coast rotating around. So there's the long wave trough in the jet stream. And then there is possibly the other finger of the jet to the north. So once you get over the United States, this thing, we do have a slight ridging, but it's mostly zonal. So there's no major ridge. We do have a deep trough over the west coast. So see what's going on over there. If there's a low, what's happening there? What's maybe a low with a front coming out of it right here, possibly. What kind of jet support do we have? Here's the jet stream. And then You can see these waves through here over Mexico moving up into Texas. That's a pretty unstable area right there. Obviously, we have a lot of instability right here in the over Texas, and then looking for the subtropical high, we have the rotation around that high. Do we see it here? I see a lot of convection over the Atlantic. I see the rotation coming in from the Gulf. So you have that southerly flow. So now you have warm, moist air advection pushing up into the Gulf states. I'm going to clear this out. So we do have a couple areas of convection here also. So we get that onshore flow. We get some instability. We do get some thunderstorms in that area. So what we're going to look for, just doing a refresh, is wind shear. We want to see if we can find the low level jet. How low does that jet go? Is that a jet finger? How low does that go into the lower levels? We can pull up a low level wind shear on. I can do that on the charts, and then we can see what kind of support we have for these systems. We'll look at the SPC, see what kind of severe weather warnings they have out or watches. See what the day 1, day 2 is on the severe weather possibilities, and then see how this system is going to develop. So, like I said, there's your long wave trough, possible front. There's a jet finger. A lot of cirrus clouds through that area. Now, if we look closely on this satellite, what we want to look for is obviously see low level clouds, but you're in the mountain range here. Look at a lot of that stuff turns blue. That's an indication of those lower level clouds too. So as this satellite continues to update, you'll see a lot more of that, because you're going to miss a lot of it where the sun goes down. So a lot of cumulus, stratus, a lot of cirrus stratus going over that ridge. So there's our long wave trough. Here's our jet finger. We need to see what's going on over Texas, and we need to see what's going on over the Gulf states. Let me get out of here. Let's go to a satellite national radar. This is in telecast. It gives us the different precipitation types, so it's easy to see where your lines are. Now, like I said, we have that long wave trough over off the west coast. Let me make sure I can draw on this screen. Alright, so long wave trough, jet finger, then we had a jet finger down here. So we seen we had that high pressure system coming around, onshore flow. There's our warm moist air. Definitely got some instability in the Gulf states. Looks like a little bit of convection was going on there for a short period. So you see that goes away. The reason that went away was the sun went down, so it lost its heating. So we did have that little area over Texas. We need to see what's happening there on the surface chart, and then we can see basically our trough. That trough was pretty deep, but if we look at this, probably higher pressure in this area. Dropping this freezing level, there's our rain snow line. So we can see that. So now we can tell we have ridging over the eastern part of the United States, over the Gulf Lakes region, and then the troughing over the west coast. So, high pressure, lower heights, maybe a cold front right there, pushing through for that high pressure system to push through, and then a lot of maybe some lake effect snow, or a little bit of shortwave troughing going on through this ridge, causing the instability over the Great Lakes. So other possibilities, like I said, we want to pull up the surface chart, see where our features are, and then, like I said, this is pretty zonal, but to see where our features are and then see what kind of support we have for these systems. Alright, so we know we got snow over the Great Lakes, snow over Minnesota, over the Rockies. That's all ridging, and a lot of this could be ground clutter, but a lot of this is, you got a lot of troughs and ridges through the Rockies, so you will have pretty much scattered snow showers like that. Your continental divide is going to drop down, so any flow toward those mountains is going to give you lift to create any precipitation along the mountain range too. So we'll get a better look at that here in a minute. Let me get rid of this. Okay, so I have my base map overlaid on radar. It's a National Weather Service radar. This is a little bit older, maybe just an hour or two. Nothing serious. So you can see the convection over Alabama, Georgia. It was a little bit stronger. Let me get my draw tool here. Alright, there's our area of convection. Here's our disturbance over Texas, and then like we said, we had all that. We were just looking at on the Intellicast radar. So all this was pretty much snow to the north. Alright, so I got the latest data downloaded. Let's go, let's create a surface chart. Make sure my settings are correct. I don't want to clutter this thing too bad. So we're going to start with sea level pressure. This is going to show us our highs and lows. Okay, so we have low pressure over Texas. Pretty much an elongated low pressure system from the Four Corners to Texas. So there's our southerly flow. Subtropical high off the east coast. There's our southerly flow. If you look at these lines, how they curve, there's a little bit of troughing in this area. This is definitely ridging. So we have maybe some minor short waves in that area. With the onshore flow, the warm moist air creating a little bit of instability in that area. So that can explain that rain and thunderstorms. So how severe those thunderstorms get, that's going to depend on how much instability. So we'd have to pull some QT charts in that area, see what the stability of the atmosphere is, and then you can determine if you're going to have severe weather or not. All right, so but for now, we're not going to really get into all that. We're just going to do just some basics here. Troughing, ridging, troughing. All right, so there's some troughing. So you can see how around this low pressure system you have trough, ridge. So you have a ridge here, trough, ridge, trough. There's going to be another ridge here somewhere, and then troughing there. So we can throw our isotherms on here. That will show any temperature advection, and that's going to show us areas of precip. If we have warm air advection, cold air advection, if we should expect higher heights or lower heights in those areas, if this low pressure system is going to fill or is going to deepen. Where the high pressure to the north is going to move to. We've seen our jet flow was pretty zonal, so any of these systems are pretty much going to be just kind of pushing just to the northeast to the east. So that's pretty much how your steer flow is going to go, just based on the upper levels. Now we'll know a little bit more on the steering flow if we go to the 500, 700 millibar. We can look at those mid levels, and that's really going to give us an idea of where the center of these low pressure systems are going to move to. First, we have to determine exactly where the center of this low is. This isn't two low pressure systems right next to each other. This is just an elongated low and maybe a little bit of lower pressure over here versus this one, and that's why the computer's putting two lows in that one area. There's definitely not closed circulation around both of these lows. That just simply can't happen. All right, so isotherms, lines of equal temperature. I use Celsius. It's every 2 degrees. if I use Fahrenheit every 2 degrees, these lines are so close together you can't even make them out. Which right now the Celsius is pretty close together, so it's really hard to make these out, which line is which. So, but we do have some pretty strong thermal advection to the north. Let's get a look at that real quick if we want to place our fronts. Just the first guess on the frontal systems. We can have one, we're looking for thermal advection. So out of this low, we know winds circulate counterclockwise around the low. With the northerly winds pushing all that cold air to the south, we know we got a cold front here. So where do we put the cold front? We got to put it, you're pretty much at the leading edge of that thermal advection. But let's get some surface plots on here, and that's going to build our chart. Let's see what give us a better idea of where we can place these fronts and what's actually going on. So once we get the station plots on, now we can pick out, we can see our lower ceilings. All the red is the lowest ceilings, the blue are still low ceilings, and then all the black are VFR conditions. All the ceilings are above 3,000 feet, or visibility is above 3 miles. So we look at lower ceilings to the south. Now let's look at our wind flow here. You want to justify these fronts with your flow. So if we had a warm front in this area, where's that warm front going to be? Let's get out of that. Let's go get the correct color on here, and then let's see, where's our winds? There's a wind out of the southwest, there's a wind out of the northeast. So those are opposing each other, so that front is going to have to separate those two winds. Now what we're looking for is a southerly wind on the east side of that low, because of the way the winds flow around low pressure system. And then we're looking for a wind shift. So once we see that wind shift to go easterly, now we can take our front up into and separate those winds. So now we have a southerly, because you can see anywhere, let me go ahead and erase that. So anywhere that the isotherms cross the isobars are the black lines of equal pressure. The red dashed lines are isotherms, lines of equal temperature. So where they cross, that is where you have thermal advection. So which way is the thermal advection going? From warm to cold. So that is a warm front. So at the beginning of that advection is where you typically place your warm front. Now, like I said, you have to go back and look at that to the detail and look at your winds. Also look at your temperatures. So we got 68 right there, 53 right there. Here's a wind shift here. I don't know what that says, 67, 42. So that's a pretty good temperature difference. So we're going to jump that warm front right around through that trough. Alright, so this is your warm sector. Anything behind that, all your warm air advections up through here, and then we got that southerly flow, warm moist air. So now, like we said, we got some minor short waves going around that high, that subtropical high, is a semi-permanent high pressure system out there. They are always there. Now, these will work their way to the north in the summer, work their way to the south in the winter, so they vary. Now, when they do work their way to the south, you end up with a long wave trough like we have here, and then a high pressure breaking out. Then that high pressure could come through, interfere with this high. Well, actually, we get a low pressure system develop. High pressure forms. Let me get this cleared out. High pressure drops down, low pressure forms as it pushes to the northeast. Then that low pressure system picks up all that moisture that this high pressure is pumping into the Gulf states, and then that's where you can get that severe weather in that area. So it's kind of like what's happening right here with that low pressure system. So if we look at this low, we want to look at, there's a little bit of troughing right there. There's some ridging right there, the way that wind's flowing. here's some serious rotation right there. So that doesn't quite close that low because you have this, which is really nothing. That is, let me look at that wind. It's maybe a 5-knot wind right there. So I kind of ignore those. You can get a 5-knot sustained wind on an ASOS or a weather observation. It doesn't take much to do that. But when you're getting into these 20-knot winds, 30-knot winds, and then you're getting rotation like that, you can almost close that low off. This one, I see the wind from the southwest. Here's a rotation. So you don't have the low here. That's more frontal. That's the frontal separation with those opposing winds. So we're looking for, typically, you're looking for an easterly flow to justify closing off that low. I don't really see that, so I'm kind of pushing that low back here with this one. You might have a little bit of a low pressure right there, you know, because the pressure is probably maybe going increasing then decreasing. Let's look at that, 1,000.2. There's 1,000. There's a 998.6, so that is a little bit lower pressure than that 1,000.2. And then to the west, we have 1,001.5. Here's 1,002.3. So you can see the difference. You got the lower pressure, a little bit higher pressure going to even lower pressure. So this low pressure system is a little bit deeper than that one. So they're both labeled 1,001 millibars. So like I said, that is just an elongated low pressure system. We definitely got thermal advection. So we would have the warm front. Looking to the back, we want to find that northwesterly flow. So your cold front would be back behind that. Right, you're looking for those wind shifts. You're looking for, here's a 65, there's a 40. Your cold front definitely stretches back there. Now, if we look at this closer, we can see high pressure. It's a pretty strong trough, inverted trough right there out of that low. Ridging. So we're going to look for, I'm going to pull the fronts up here in a second and see where they go. The front's not going to go that far out into the high pressure system unless you want to separate two high pressure systems. Then you would, you know, pretty much go stationary, which this is a pretty zonal flow. So we've seen that deep trough, and then that one's pretty zonal. So our systems aren't going to be moving very fast. Now, this low pressure system could push to the northeast a little bit. We'll have to see how fast that moves. I think it's going to take a few days to get across the U.S. I don't think this thing's going to shoot over like in a day or two, like they normally do. So I think it's going to take a little bit longer just because of that flow. We'll have to look at the low level winds, see what kind of speeds we got too. With the zonal flow, it could even be a faster travel on that. Typically when you're looking at with this ridging, you're looking at the high pressure pushing through, and that's justifying the cold front. But if you had a cold front back here, we had that troughing, so your high pressure system's well off the west coast. Let me get out of this and let's look at our fronts real quick. This will pretty much clutter this thing up. So, all right, what do we have here? We got the high pressure system to the northeast. Get back in here now. There's your high. Here's the leading edge of that air mass. Pushing into that trough, so kind of a cold front into that area, which doesn't make sense a whole lot just because, I mean, we definitely got, I would say the cold front's there, but it's not coming back that far into that trough because you have too much warm air advection. If you have warm air advection, winds are right here, out of the southeast, out of the south, that's warm air advection. You're not pushing up against that cold front. So that's wrong. Let's call the front here. We can go a little bit past that line. Doesn't have to stop at the line. So we can call cold front, and then we're going to have to go either with a warm pip and go stationary, or just go straight into the warm front. And like this is all, this cold right here, don't care for that. That low pressure system right there, don't really care for that. Let's get a good look at that though. Clear this off, because this is developing a low over Iowa. Now we do got the north westerly flow going to a southerly flow. There's a easterly flow, so you could almost put some rotation right there. So then that would kind of justify a little bit of warm air advection there, which all that warm air advection is justified. This cold pip right there, that can pretty much go away. I would tie that right into the warm front. But then you have another problem. You do got winds blowing out of the high pressure system, so you could almost go cold right there. Let's see where our temperatures are. There's a 42, there's a 10. That's a pretty strong temperature change. There's 23. Can't see that one. 57, 67, something like that. I see a 7 in there. So maybe a little weak cold front right there. It's just with some cold air advection. I don't know if I'd necessarily call it a front. There's our wind shift. That's definitely warm air. Still got that southerly flow, so we still got the warm air advection. I'm almost pulling that into that. If we have one cold pip here, we might have a little bit of rotation right there. We'll have to see how that develops on the models, if it's picking that up. We know our jet stream was deep, going zonal, so kind of gives it that support along that front. So that does kind of make sense there. Plus our tightest part of our thermal gradient is right through this area too. So that's where your jet stream would most likely be. This is placing a trough right through this area over Texas. That's what's causing that disturbance and all that that precip. Like we said, we had onshore flow here. We could almost place a little bit of a trough in this area, justifying that precipitation. Clear this out. So when you got a big giant area of low pressure like this, as you can see, it's hard to pick out that as a low pressure system just to say, okay, that's one low pressure system, you know, the mother storm that's just going to push to the northeast. You could have a low right there. That we made sense of that one. We made sense of this low right there. Let me get out of here. See, like I said, this, when I put the fronts on here, it clutters up with highs and lows. So it throws lows where there are just troughs. But we did justify that low. Seen a little bit of rotation on that one. We justified kind of that low. So just some isolated lower pressure systems here. Does not make sense to have low, high, low right in that area. But when you got a big system like this, you got to start picking out those troughs and ridges and find out exactly what's going on. So we got that big area of low pressure, a bunch of short waves going around this low. So you can pretty much get precip anywhere around that low that's needed. Right here, if we look at the continental divide, now we can see those ISO bars are pushing perpendicular to the mountain range. So now you do have some lift and instability to justify these this precipitation. And then we've seen all those areas of precipitation over the Rockies, so that pretty much justifies all of that. And then this ridging, Great Lakes region, pretty much your moisture source. Inverted troughing, that justifies all that precip, and we are well to the north above the freezing level, and I'm sure the 540 line, that's going to drop down around that high. We'll have to see exactly where that is, and we'll justify that as snow. So I'm going to clear this chart. Now we're going to build a thickness chart. Alright, so if we can see on that, here's our 540 line, the purple line. That's the rain snow line. And that's pretty zonal along with that jet. Because your north-south temperature gradient is what causes the jet stream. So we know we had a long wave trough down over the west coast. So, and then we went pretty zonal. So that kind of makes sense for that rain snow line to be pretty much flat. And then anything to the north of that's going to be snow. Anything to the south is going to be rain. So we could pretty much justify that as snow. That does work out for this one. So there's one symbol. It looks like some heavy snow. Possibly even some heavy rain right there. Let me see what we got. That just looks like snow symbols. That's definitely snow. And then this is a moderate rain. Some light rain. So if you look at those weather symbols, you could tell, if you learn how to read these station plots, you could tell what type of weather you're having at those stations at that time. This is pretty much are done on the hour, unless it starts raining between the top of the hour. Then they have to do a special report and send out a special observation to start the rain. So if you look at one of these station plots, try to find one that's pretty clear. So like this one, top number is 33 degrees. Bottom number, that's your temperature. The bottom number is 16, that's your dew point. And then the number to the top right corner is your station pressure. And if you see a 0 there, you're just going to add a 1 in front of it. So you see, you're going to add a 10 in front of it, sorry. So that's 1007.3. 1007 millibars. If you see a 9, then you're going to add a 9 in front of it. It'll be 998.6 millibars. Now the C120 to the left of that, actually it's down to the bottom right of this station right here. That C120 is your ceiling is at 12,000 feet. It means it's broken. At least 5/8 of the sky is covered. And the lowest ceiling is 12,000 feet. This, just to the left of the station, like these two lines, that is mist. That's your weather just to the left of those stations. So like I said, we've seen those ones. Where'd it go? Right here, snow. Just to the left, you see 2 snow flakes. That's light snow. If you see 3, that's moderate snow. If you see 4, that's heavy snow. Like this one right here, it's heavy snow. Light snow. And then the colors right there are with the red stations, that is a IFR conditions. That is instrument flight rules. It's for aircraft, and the ceiling is below 1,000 feet, or visibility is between 1 and 3 miles. The blue is marginal VFR, and that is the ceiling is between 1,000 and 3,000 feet, and the visibility is between 3 and 5 miles. And then you have VFR conditions, which is the black. That's visual flight rules. And those, the ceiling is greater than 3,000 feet, and door visibility is greater than 5 miles. So depending on the visibility, can drop you down to an IFR condition. You can still have high ceilings, but still have low visibility, and that can change the rules for aircraft. So that's really, it's all that's telling you. But from a weather forecaster standpoint, you could say, all right, we have pretty low ceilings here, all through here. This is where most of our low cloud cover is, or low visibility. So you either have precip in them areas, or you have low ceilings. Low visibility, low ceilings, and then medium visibility and ceilings where the blue is, and then you still got a cloud cover where all the black is, but it's the ceilings are a lot higher. The visibility's either unrestricted, or it's at least greater than 5 miles. So that's pretty much all you need to know on that one. Now, like we said, we had some troughing going on through here, a little bit of lows, troughing. So let's go to the upper levels. Let's see how long this video is. It's getting pretty long already. So I may just do another video on upper level charts. Let's go to the jet stream real quick. I do want to look at the jet. We want to verify that jet, how it supports its low, where it is, and we might as well just go to the mid levels, because if we're going to start looking at the jet stream, look at this low pressure system, we want to see how this is supported, how far in the upper levels this low pressure already goes, and then see what kind of jet support it has, see what our steering flow is, and then justify these intensities. So if I keep going with the charts, this video can get pretty long, because I was wanting to jump into the models too. So I'm not sure what to do. I'm going to hit the jet stream, just show you on the jet real quick. I'm going to have to clear this chart off completely. We're going to go blank so we can see our jet stream. Let me erase that, and we're going to recenter. Alright, let's get let's get our symbol back on. Now we got a blank chart we can look at, and we are going to go to the 300 millibar. Now we're going to pull up our different colors for different wind speeds and see where our jet streams are for jet fingers. So we got a jet Maxwell to the north. Got a pretty good strong little bit of finger to the south, so that's kind of supporting that precipitation that's to the south. With that low pressure system, it's over Texas, so that's giving that support. Put on our heights. These are contours on the upper levels, so it's lines of equal height. I want to do a balanced the balanced contours, because this one's not really showing us our troughing off the west coast. Since it's not showing that, it's not going to be 100% accurate. We see that on the satellite, so we know it's there. So whenever I see this on the charts where it doesn't give me my trough, then I want to Just change a little bit of settings here. Takes a little bit longer to plot, but I want to change the settings so I can see. I want to be able to see that trough, so we get a more true picture of the upper atmosphere. Just be a second. Then we need to turn up the station plots too, because the balloons that are released are there's not as many as there are weather stations on the surface. So we want all the data we can get. This does give us a little bit tighter gradient, so kind of ignore that. But we do have a strong, thermal gradient there anyway, just because, at least the pressure gradient, because we have a pretty strong jet max well to the north. So we can break down this jet max too. I think I might just do that for you in this video. So I won't get into the mid levels, I don't think, and then into the models. I'll have to do that on another video. But right now, let's just get into a little bit of a learning phase. So we got looks like some warm core system here. So the cold air is to the outside, warmer in the middle. So we got a warm pocket in the upper levels. We have, typically when you get in the upper levels like this, you get these isotherms get more parallel to the contours, so you don't really have any thermal advection. But you can see off the west coast where that deep trough is, that we do have a little bit of thermal advection there. So at and ahead of that front, we can have some upper level clouds and stuff like that. I mean, we're at 30,000 feet, so we don't use this for the surface and say, okay, we're going to get a low form up right there or anything like that. But just look at the contours. When you get thermal advection that high up, you have support for something. You have a long wave trough, you have support. We had that low pressure system kind of over Texas, over the Four Corners area. So back behind that, we have a long wave trough with thermal advection. So that supports that low there. So you'd have to get into the mid levels to break that system down. If this trough even isn't just an upper level trough, or is that low pressure system that intense? We know it's a pretty big system, but is it that intense it's going all the way up into the upper levels like that? We do have a warmer pocket here, so that could be an indication of that low pressure system being kind of a warm core low that's formed up and actually stacked up toward the colder air in the upper levels too. So because you're troughing in your low pressure system, as it stacks back, it's going to always stack back toward the colder air. Now looking at the intensity of that jet max, we got a pretty good strong jet max there. We're gonna have to look at, we'd have to go down and look at this jet max. It's a lot weaker, but go down to the surface, go into the 850, the mid levels, and find out, break that thing down too. If you watch this video to this point, leave me a comment about which one we do. I might just go live, and we just go live like for about 3 or 4 hours and just go from the surface to 30,000 feet, maybe even higher. We can go up to 40,000 feet, and then look at our jet stream, break it down, look at the low pressure systems. Maybe what I'll do is pick a good system that comes through, and we got that low pressure system that's over Texas. We'll have to see how that develops and where it moves to, but over the next couple days or few days, we may have a good system to work with. So if I have time, see what happens on the weekend, and I'm off next week, so I might just take one day next week and do a pretty long video. Like I said, at least comment so I know somebody's out there at least watching, and if they want to go that deep with it. I can go 3 or 4 hours pretty easy. So let's just hit this real quick. Let's put the station plots on here. Now I'm at pretty much 100% of all the balloons that are let go throughout the United States. Now this thing is going to show us our wind speeds. A lot we can get off of this jet stream. So let me get back into the draw tool. Okay, so first thing we see, got a pretty good jet max right here. I mean, not really a pretty good jet max. I mean, you got 80 knot winds, 75 knot winds, 85 knot winds going into this thing. Now up here you have 100 knot winds, 120, 130. There's 150 plus. That looks like 120, but you're pushing 150. It looks like right there, that in that area. So we clear that out. That's not really. That's about 120. That's probably 125. Your strongest winds are going to be in that purple. Let me get rid of this for a second. Let me pull that up here. So we don't have a whole lot of data up there. There's 125 knot winds right there. There's another 125. So this was all kind of cluttered together. That's about 120 on the outside of that jet max. Now if we look at this jet max real quick, what we want to learn is that we got, let me get to a page here. I want to break this down for you just a second. For the different quadrants of this jet max, let me get back in here. I'm kind of going to break this down to quadrants. So 4 quadrants of the jet max, you're going to look for, you're going to have convergence aloft in the top left quadrant, northwest quadrant of that jet max. You're going to have convergence. That means the winds are coming together, which they're not blowing together like this, but you do have upper level convergence, which would be more of like a speed convergence. We don't have a lot of data up here to prove it, but if you have winds coming in, say that's 100 knot winds there going in, and then you have out of that quadrant of the jet, say you have 75 knots going out. Now these numbers are not accurate. Like I said, we don't have any data. We know we got 125 knot winds through the center of this jet max, so this is just for educational purposes. So 100 in, 75 out, you have speed convergence. You have more going in than you do going out, so that's going to create a downward vertical motion in that quadrant of the jet. That's typically what happens in that area. In the northeast quadrant of the jet, you're going to have divergence. So you're going to have that 75 knot wind going in, and then 100 knot wind going out. Now you got more going out than you got coming in. That's going to create an upward vertical motion. So now you have upper level divergence. So that area of the jet max, you're going to be divergent there, convergent there, divergent in the southwest, convergent in the southeast, the quadrants of this jet. Now when you have this support, when you're looking at a thunderstorm, the southwest quadrant of the thunderstorm is where you get the tornadoes. That's on the back side of that system. Now if you have a jet stream come up supporting that low pressure system, you got a cold front, you got all the weather at the head of that cold front or at behind that cold front, depending if it's an active inactive cold front, then you're going to have the thunderstorm cells tiny, but you're going to have that southwest quadrant of that thunderstorm cell that's going to create them tornadoes. Now if you have a jet max going through, then in that southwest quadrant of that jet max is over that thunderstorm, then you're going to have upper level divergence, and then you're going to have, I'll give you a better picture of that one, but then you're going to have upward vertical motion and support for that thunderstorm or that tornado to become even more tense. So that pretty much breaks down, not all of it, but just a quick reference on your jet max where your convergence and divergence is associated with that jet. Alright, so if we look at this thing, let me get rid of all of that for a second. I'm going to throw those heights back on there real quick. Then I'm going to throw the surface pressure over top of that as a composite chart. And then we'll look at that real quick. So we're coming up on an hour. I'm pretty much going to do this, and I'm going to call quits. Like I said, give me a comment if you want me to go even longer. I can do a live stream and covering the models. If we cover the charts, satellite radar charts, models, all the way through, we can go for several hours. So, all right, we see our long wave. All right, there's our long wave trough. All right, turn it off for a second. Let me get to the surface. All right, so if you see the low pressure system, you see the long wave trough. There's our trough at 30,000 feet. This low pressure system, you had a cold front on the surface, which that cold air advection was kind of pushed a little bit further, more westerly. But with this trough, here's your jet stream. That's what's going to have to support that front. So that front's going to have to kind of wrap around that. The jet stream's not going to cross the front. Okay, so there's our trough. If we brought that front there from the surface, then the 850 would be either an upper front or a trough. 700 would be, you can even have a, depending on how steep that slope is, that cold air mass going up, then you can even have an upper front on a 700. Most of the time you don't. You just have a trough supporting that. So you go to the 700, 500, and then you go to the 300. And then that troughing stacks back to the colder air, supports for this low pressure system, jet stream. Stays north of the fronts. Now you have your jet support. You have a jet max, like we talked about with the quadrants of the jet max, supporting that low pressure system, upper level divergence. That will support that low. And then isolated thunderstorms throughout that, along that frontal system, and where that jet max is, what quadrant of the jet max is over those thunderstorm cells or over that low pressure, what kind of support you have there. All right, so like I said, this gets messy pretty quick. Let me get out of that, and we will go to our models real quick. All right, so this is wind speed. I want to go back to the surface. All right, there's the low pressure system. Right there's one around the four corners. We'll keep an eye on that one. That's the low that's there, then elongated over into Texas. So let's see how this low pressure system develops. We have all that snow over the Rockies, snow well to the north, our precipitation to the south. So these are verifying pretty good. We have that inverted trough all the way up through the Midwest into the Great Lakes region. We have the high pressure system, semi-permanent high, ridging over into the Gulf, and then we have our southerly flow with our warm moist air advection up into the Gulf states. Alright, so watch the low moving down over Texas. So if we go back real quick, we got this low right here. It's kind of just a troughing and some low just kind of sitting around there. This one, let me go back, get to the beginning. Got that low kind of pushing up pretty quickly up into Tuesday, causing a lot of precip through the Ohio Valley. Looks like the high pressure system does drop down pretty quick. And then we have another trough or area low pressure develop over Texas, and now there are definitely, with the high pressure system pushing south, there's our rain snow line pushing well to the south too. So now we have a more developed low pressure, and that looks like Thursday into Friday morning, and then causing a lot of precip over the Great Lakes region further south, and the looks like some ice and freezing rain right there throughout the Ohio Valley. So let's go back. looks like freezing down into Texas. Freezing rain, Oklahoma, pushing up into Missouri, Illinois, Indiana. That line just kind of hanging on down there because that high pressure just pushing that far south. Let's just see what happens there with that cold air dropping down off the mountains. That's what's going to be causing that freezing level to drop like that. And then got that line pushing through for Thursday, Friday, through the Ohio Valley. And that could be a significant amount of snowfall to the north and a significant amount of ice and freezing rain in the Ohio Valley. So that's going to be interesting to keep an eye on for all the way up into Columbus, Dayton, Columbus area. And then it looks like for Friday morning, that low pressure system pushes off, and then the northeast getting hammered once again throughout Vermont, New Hampshire, Maine. And then that low pressure system, still some mixed precip right there through Pennsylvania. And kind of a lot of that icing disappears once it gets past once it gets through New York. And then it looks like it's mostly snow in the northeast. So we'll go back, keep going back, and we'll have to keep an eye on this area here for any significant weather. So that's for Wednesday, Tuesday into Wednesday, and then another frontal system pushing through right there. The high pressure drops well to the south. Like I said, I like to pull some temperatures, break down that high too, see if this does make sense. I mean, we are still in February, so February is usually the worst month for Ohio. Finally get some significant precip, and then it looks like some scattered snow showers all along the Great Lakes region and the northeast. So a little far out on that 141 hours. So I'm going to end the video right here. Like I said, leave a comment if you guys want a live stream breaking down systems beginning to end, real-time data and forecast data like this. If we do that, we're just going to go all the way with it. We're going to start from the surface, break our systems down all the way up to the upper levels. Then we're going to come over to the models, and then we're going to break down those systems in the models and pull upper level models and see how the models develop as far as support for systems that go through, and which models we use, why. I'm not a real big models guy, except for it is a tool. That's what it is. I don't forecast straight off the models. I do use them as a strong tool, but they got to make sense. You got to know what you're looking at for atmospheric dynamics. They got to make sense, and then that way you can say, okay, we're going to stop it right there. We're not going to go any further as far as, out with the forecast, because that system's just getting too far deranged. So, all right, I'm going to stop it here. This is went on long enough. So, like I said, leave me a comment if you want to learn a lot more, and then let me know if you want me to do a live stream. I'm going to try to start doing some short videos. See what I can do, like maybe some YouTube shorts or something, I don't know, on just weather systems, quick, 1 minute or less kind of stuff, just learning some atmospheric dynamics. We're trying to keep this thing basic. We don't want to bury you guys too much into atmospheric dynamics, physics, stuff like that, and it just gets way over the head, and people don't even care. So let me know what you think. Thanks for watching. Visit my website, meteorology101.com. And until next time, get your head in the clouds.